Okay, let me share my screen now. Um, what are you seeing? Are you seeing a PowerPoint presentation or the Canvas for now?
PowerPoint.
Okay, the PowerPoint. So I need to share first the Canvas. Is it now the Canvas that you are seeing? Let me share again, class. Ha? Do you see my Canvas screen already?
Yes, Miss.
Okay, so I will just click here on convections. Before I go to the slides, because it gives you an overview of the new topic, which is the second mode of heat transfer, which is convective heat transfer. Okay, when we speak of convective heat transfer, we often refer to it as convection. Now, it is the transfer of heat from one place to another by, so take note, there has to be movement of fluids. Now, convection is usually the dominant form of heat transfer in fluids. Now, specifically when we speak of liquids and gases. Although often discussed as a distinct method of heat transfer, convective heat transfer involves the combined processes of, so oftentimes it does not stand alone, but it also involves conductive heat transfer, that is through heat diffusion, and this new term here, advection. So heat transfer due to the flow of the bulk fluid itself. So when you speak of convection, we have in mind purely that there is to be a flow of, or there has to be flow of fluids, whether it's liquid or gases. But specifically, class, it does not stand alone. So it is in reference to, or it adds up to it, what we call conductive heat transfer, or that is heat transfer through diffusion and advection. So heat transfer by the flow of the bulk fluid itself. Now in here, we have a new property of material that we will look up into a particular property table. May it be our Paris Chemical Engineer's Handbook, or if you have your book by Gian Kuplis or McCabe, you can look at it in the appendices. Okay, so this particular characteristic is what we call the convective heat transfer coefficient, or that is the H. Now in solids, we have it represented by K, or that's the thermal conductivity constant. Now this defines in part the heat transfer due to convection. So the convective heat transfer coefficient is sometimes referred to as a film, that has something to do with the film coefficient, and represents the thermal resistance of a relatively stagnant layer of fluid, which I have mentioned already, between the heat transfer surface and the fluid medium. So the reason behind actually why we have this pair of conductive heat transfer and convective heat transfer occurring as one, it's because we have a solid in which a fluid is passed through. So in that case, now you have to consider that particular film or coating that offers resistance to heat flow by the bulk of fluid, or the fluid as a bulk flowing against the surface in which is normally heat is passing through, and that is heat through diffusion. So this particular film coefficient offering resistance to flow is accounted for by this particular convective heat transfer coefficient. So commonly used units to measure the convective heat transfer coefficients are the ones that you are seeing here. So the most common is the watt per square meter per Kelvin, So it has its equivalent here in BTU per feet squared per hour per degree Fahrenheit, as well as another set for the SI units, which is kilocalorie per hour meter squared degree Celsius. Let me just check the inbox class. Okay, thank you for putting in your names for the attendances. Now, as to BTU per hour converted to watt per square meter Kelvin or kilocalorie per hour meter square degree Celsius, you also have this. But the most common is this one, the watt per square meter Kelvin, and the one in BTU, BTU per hour per feet squared per degree Fahrenheit. Okay, now convection involves the transfer of heat by the motion and the mixing of macroscopic portions of the fluid. That is the flow of a fluid past a solid boundary. So again, reiterating that it's always a pair. Conduction in the solid boundary and convection on the bulk fluid itself. The term natural convection is used if it's this motion and mixing is caused by the density variations. Take note, is caused by the density variations resulting from temperature differences between the fluid. The term forced convection is used if this motion and mixing is caused by an outside force, such as a pump or a ventilator or something that has blades which pushes your fluid to flow faster against the surface in which it is flowing on top of or adjacent of. So again, notice here that there are two types of convective heat transfer. We have natural, meaning it's not induced, and we have forced convection, which is induced through the use of pumps or impellers. Now, the transfer of heat from a hot water radiator to a room is an example of heat transfer by natural convection. So there are no pumps mentioned. There were no blades to hasten the transfer of or to fan off the or to, let's say, to induce the flow of air against this particular radiator. There's nothing mentioned about that. So it's natural convection. Whereas the transfer of heat from the surface of a heat exchanger to the bulk of fluid being pumped, so take note of the word pump, through the heat exchanger is an example of forced convection. So we have two types of convection. We have the natural convection and we have the forced convection. Now, heat transfer by convection is more challenging, if I will use an appropriate term, is more challenging or difficult to analyze than heat transfer by conduction because there's no single property of the heat transfer medium, such as thermal conductivity, that can be defined to describe the mechanism. So heat transfer by convection varies from situation to situation upon the fluid flow conditions, and it is frequently coupled with the mode of fluid flow. In practice, analysis of heat transfer by convection is treated empirically, that is by direct observation. Now, the treatment of heat transfer by convection in itself being stated here as empirically is because it's dependent on formulas that were also based on empirical data. So before, unlike conduction that we can directly use the formula that Fourier provided for us, in the case of convection, there is still this challenge of, let's say, for example, reading from a particular property table the properties that we will place in a particular formula. And there is still a need for us to test whether the flow of the fluid that we are given is on the laminar flow, on the turbulent flow, or somewhere in between the boundary of laminar and turbulent. And I guess you have already studied before how to determine whether the flow is laminar or turbulent. So in here, we'll be using again those formulas that you have encountered in testing which flow regime your fluid is classified. Now, convection heat transfer is treated empirically because of the factors that affect the stagnant film thickness. So among these factors are the following. So what's indicated here are 5. So we have the fluid velocity, the fluid viscosity, and when we speak of the viscosity class, it could be the viscosity near the wall, or it could even be viscosity of the fluid, the bulk fluid itself. Then we have the heat flux. Then we have the how rough is the surface in which the fluid is flowing against or adjacent to, and type of flow, whether it's single phase or two phase. In our case class, we classify the flow in here based on the formulas that we are using as either laminar or turbulent. Once we have classified it properly already, then that's the time that we substitute the appropriate H to our formula for convective heat transfer. Now, convection involves the transfer of heat between a surface at a given temperature T sub 1 and the fluid at a bulk temperature T sub B. So the surface temperature is labeled as T sub 1, and that of our fluid is, of course, it has here the subscript B, referring to the bulk temperature. The exact definition of the bulk temperature varies depending on the details of the situation. So for every situation, for every type of diffusion, we have an appropriate formula to use in the case of convection. Now, for flow adjacent to a hot or cold surface, T sub B is the temperature of the fluid far from the surface. For boiling or condensation, T sub B is the saturation temperature of the fluid. For flow in pipes, T sub B is the average temperature measured at a particular cross-section of the pipe. In our case class, if you read from our general reference book by Jean Couplis, the flow in pipes is often given as an example, and most problems are concentrated on flow in pipes. And the bulk temperature is the average temperature in a particular cross-section of the pipe. Now, in here, in this part of your canvas, I placed already, although I've shared in the PowerPoint, the formula for convective heat transfer, the basic fundamental formula for heat transfer by conduction or convection, which is using this time your heat transfer coefficient, specifically the convective heat transfer coefficient, the surface area for heat transfer, and the temperature difference. Now in here, the set of units indicated are English units. So our Q in here class is heat transfer rate. So meaning its unit is joule per second when we speak of a set of units in SI. Okay? Or it could be something like this, where your Q is the heat transfer per unit time, which is already the watt in joule per second, and your area is in square meter, and your H of C is the convective heat transfer coefficient of the process. Now notice class that your H of C here, your H of C is different in set of units than that of the thermal conductivity constant, because in this case you have the heat flux, the rate expressed per unit area, and then you have it also measured per unit temperature, absolute temperature, which is in Kelvin. So this is your set of units for convective heat transfer coefficient. The temperature of the surface is T sub S, equivalent to T sub 1 here. Where is it? Mentioned here, the T sub 1, the surface temperature, and you have the temperature of the air in the case of the fluid adjacent the surface, flowing adjacent the surface if it's air. So that would be T sub A, or T sub B if it's not air. So the convective heat transfer coefficient H is dependent upon the physical properties of the fluid, take note, and the physical situation or the condition that is. So typically, the convective heat transfer coefficient for laminar flow is relatively low. Take note of this as well, compared to the convective heat transfer coefficient for turbulent flow. And as such, it is important always that we establish what is the flow regime concentration of our fluid before we even substitute the appropriate H to our formula or to our basic formula, which is this one. Okay, now values of H have been measured and tabulated for commonly encountered fluids and flow situations occurring during heat transfer by convection. And that could be found in your Paris Chemical Engineer's Handbook. You look for it in section 2. And it could also be found in our general reference books, either by John Kuplis or McKay. Okay, so these are the informations that you can read or that is posted in your Canvas regarding the intro, or let's say an overview of convective heat transfer. As to the specifics class, I've placed in here the 3 sets of PowerPoint presentations already in PDF, which will I go through one by one today, starting today. So I have divided it into 3 different portions because part 1 is for, I think, natural convection. Then we have forced convection divided into these 2 PDF copies of the slide. But before I go to this, do you have any questions? By the way, the one that you are reading here, this one, because I love the overview that is provided in a particular site regarding convective heat transfer. So it's taken from engineersedge.com. Now, whereas this one, your PowerPoint presentation is already from, basically majority is based on Gian Kuplis, our main reference book that is being used on this topic, which is of course one of the 2 reference books that is suggested by PRC. The other one is McCabe. So for now, do you have any question here before I go to the slides? You have none? Okay, so I will now share a new slide. Let me check part 1. Okay, so this is my part 1 slide, where I tried to insert the prayer video a while ago. Can you see the slide?
Yes, miss.
Okay, so this is for forced convection. So in here, we will classify weight class because I think, again, the upper part of the slide is not shown. I don't know why. So I cannot, okay. I will just show it like this class anyway. Now, again, there's a reiteration in this slide as to the basic formula for convective heat transfer. So you have the H, you have the bulk temperature or the average temperature, and you have the wall temperature T sub W. Now, the way I represented here, class, the subscripts for the T's is the way it is represented in Gian Kuplis. Okay, so in the overview that I've read to you a while ago, the wall temperature is given as T sub 1. So, and the bulk temperature is given as T sub B. Okay, but in Gian Kuplis, this is how we represent the 2 temperatures. Okay, now classification of convective heat transfer, it's already, sorry class, it's already in here. Free or natural convection, so motion of the fluid results from the density changes in heat transfer caused by the temperature difference, as read a while ago. And forced convection, the fluid is forced to flow by pressure difference through the use of pumps or fans, also mentioned already. Now, factors affecting the convective heat transfer, there are 4 that are placed in the slide. So the physical properties of the fluid, the type and the velocity of flows, the temperature difference, and the geometry of the specific physical system. So these are actually the reasons why there's a lot of things to consider when we solve problems regarding convective heat transfer. It's not as simple as conductive heat transfer. Now let me go to the next slide. So Resistance is occurring at the surface of the solids in contact with fluid. So this is our formula. So T of the surface and T of the fluid. And if you look at the formula this way, it's not clear what is the driving force and what is the resistance. But if we rearrange the parameters and the variables that appear in our equation, you could see right away that if I place the temperature difference in the numerator, and in the denominator I place the reciprocal of the product of the convective heat transfer and the heat transfer area, then that tells you right away that this is your driving force, the temperature difference, and the reciprocal of 1 over HA is your resistance to flow. So, but in most of the time, class, this is the way it's written. This one is just to illustrate again the fundamental general principle of heat transfer, that you should have the driving force and you should have the resistance. So this is your resistance, this is your driving force. So your H here is a function of system geometry, fluid properties, flow velocity, and temperature difference. Now, your H cannot be predicted theoretically most of the time, and empirical correlations are available to predict its value. So I will show to you later a series of formulas which are empirical correlations. That way we can find the H, or we can predict the value of the H. Now, term film coefficient refers to this thin, almost stationary layer of film or fluid adjacent to the wall, which presents most of the resistance to heat transfer, and which is also accounted for by the heat transfer coefficient. Now, the conversion factor for heat transfer coefficient was also presented to you in your Canvas overview, so I will not anymore read it. But for plane wall geometry, this would be our heat transfer rate, okay, in convective heat transfer. Now, in this case, class, if you look at on top of my slide, it's already written here, combined conduction and convection. If you recall one of the sample problem I gave you, which already combined conduction and convection, there is this middle term in the denominator which accounted for the resistance offered by the film of fluid adjacent to the wall of adjacent to the surface or to the wall in which heat is to be transferred from or to. So in this case, you could see now in here, you can see now in our formula that we have H here and H here. So meaning in this case, we have resistance in one side of, let's say, the wall, and another resistance on the outer side of the wall. This could be labeled as H sub I, and this could be labeled as H sub O, inner and outer convective heat transfer coefficients, or it could be labeled as H sub 1 and H sub 0. Now, where is the conductive resistance that is being accounted in here? Because we're talking of combined conduction and convection. The conductive resistance is in the middle term. I think it's very easy to check which is a resistance accounting for conductive heat transfer and which are resistances which is accounting for convective heat transfer. By the fact that you are seeing here a K, this is conductive resistance already, and you have the thickness here. By the fact that you are seeing here an H, this is already convective heat transfer resistance that are being accounted in the case of this first term here and this last term in here in the denominator. So your denominator in this particular formula, class, accounts for both conductive resistance and convective resistances. And this is your total resistance as a whole. Your numerator is your driving force, the difference in the temperature. So this must be inner temperature and outermost temperature, T sub 1 and T sub 4. Anyway, you will have a particular sample problem which will illustrate the use of this particular formula, in which you have accounted for both conductive and convective heat transfer. Now, this one, class, if you notice, equates to another formula which already has the U. the A and the delta T over all. This U actually is this one. Okay, the U is 1 over 1 over H1 plus delta XA over KA plus 1 over HO. So we call this U as the overall heat transfer coefficient. When we speak of combined conductive and convective heat transfer class, it could be that you're using this formula, or it could be also that you can use this particular formula depending on what the problem provides. There are problems that provide you with the U instead of these individual values of the H, the K, H1 rather, the K, and the HO. So if it gives you the overall heat transfer coefficient, then the formula for you to use is this one. But you have to take note that this overall heat transfer coefficient is also equivalent to this. So as to which of these two formulas, which are equivalents of each other, are you to use, it depends really on what the problem provides. Now, I hope you have by now a copy of Giancu, please, even if it's just a soft copy, because these formulas you could see there in the sample problems that he is presenting as well. Or if you don't have Giancu, please, then McCabe would do, but it's not as easier, it's not as easily understood as Giancu, please. Okay, let me proceed. Now, if we have a cylindrical surface in which there's a fluid flowing inside and outside of that particular surface, then our Q, the heat transfer rate, is given by this particular formula. So notice that you have outer radius and inner radius here, and you have HI, inner heat transfer coefficient, and outer heat transfer coefficient. This depends on the fluids that are found on the inner part of the pipe and on the outer pipe of the pipe. Why am I saying pipe? Because you have here a cylinder. So your geometry is that of a cylinder. Now, specifically, this formula can be written as well in this form. Okay? Wait, class, huh? Okay, so this is your specific formula for that class. Now, let's go to the next slide. Now, in here, we need to find, or we need first to establish the flow of our fluid before we can even, let's say, appropriately substitute the heat transfer coefficient. Now, we have this particular empirical formulas that will point out to us the value of our H, the heat transfer coefficient here. Now, we have the Prandtl number. I think this is not something new to everybody because I'm sure this was presented already in transport. And we have another formula for the Prandtl number here. So defined by this particular rational or ratio of two, a set of so say definition of the products of the terms that you are seeing in the formula. So the numerator represents the shear component of diffusivity for momentum, meaning the product of the CP and the viscosity represents this one. Whereas the denominator represents the diffusivity for heat and relative thickness of the hydrodynamic layer. Near Prandtl number can also be represented in this form. So either you use this formula or this formula for your Prandtl number. Actually, if you look very closely, if you cancel the densities here because they appear both in the numerator and the denominator of your rational expression, this one will only be this. So I just wrote this one, that way you will see the result if these two shear component of diffusivity and diffusivity for heat and relative thickness be taken as one term or one entity. So you cancel the densities and this will be the simplified form of the formula. Now, another formula that we can use is the Nusselt number, which is used to relate data for heat transfer coefficient H to the thermal conductivity K of the fluid and the characteristic dimension D. Okay, so you have the Nusselt number here. Now, here you already see the the heat transfer coefficient H. Oftentimes, class, dirita siya ginakuha ang aton H from the formula of the Nusselt number. We solve the Nusselt number value, we equate it to this equation. That way we can get the H that we will substitute to our basic formula for convective heat transfer. Then we have the Reynolds number. This one is very common. This tells you of what is the flow regime in which a fluid could be classified to. So you have the D, the V, the rho, and the mu for the Reynolds number. Okay, now in the next slides, you will see the other empirical equations that could be used, but class, they are not common. They are not commonly used. Those that are common are only these three here: Prandtl number, the Nusselt number, and the Reynolds number. But just in case you will encounter them later on, please check as well in your handbook what's the equivalent expression, or specifically, where can you find these particular expressions in the handbook. So we have the Gratz number. So you have the Ng sub C, and these are actually, this is actually a function of your Reynolds number and your Prandtl number together with the diameter and the length of the pipe that we're talking about. So you could see it in here in the formula. Then we also have the Fourier number. Now you have this particular formula for it, and we have the Peclet number, which is just like your Gratz number, is a function also of Reynolds number and Prandtl number. Now, there's no point, class, in memorizing this. What I'm always emphasizing to my student is you should know where to find this formula in your handbook, because these are a lot of formulas to memorize. So in your case, since you have everything in your position, during the quiz, during the exam, and even during the board exam to use, your handbook, that is the primary reference material that you will be using. Please, please, please look for this already in your handbook. Where can you find it? And familiarize, or let's say put ears in your handbook where you can find this particular equation. So of course, it would be under heat transfer, and that's convective heat transfer. Or this could also be found, class, in transport of fluids in pipes. So these particular numbers, they are important because there might be problems later on that will be using them, not the common numbers that I have presented to you in here, which is the Prandtl number and the Nusselt number. Okay, these three are not so common. Now, we go now to, I said we need to establish the flow regime where our fluid falls. So if it's laminar flow, you know that the Reynolds number should be less than 2,100. In the case of fluids inside horizontal pipes. Now, this particular empirical, again, another empirical equation is credited to Sider and Tate. So all the parameters that you see, the variables that you see in the formula are defined in here. So this is your Nusselt number, which is giving you already the convective heat transfer coefficient H here, which you will be needing in the formula. Now, where is or when do you use this particular formula? This is applicable for, take note, NRE, NPR, D over L products. So product of Reynolds number, Prandtl number, and D over L ratio, which is greater than 100. And this is plus minus 20% for Reynolds number, which is greater than 10. Now, what do you mean by this, Miss? What have you written here? The formula that you have in here is applicable only for laminar flow in horizontal pipes. Aside from that, it should also conform to this condition that is stated here. If not, the value that you are getting from this particular equation should be either, or you should already like think that the value should be plus 20% or minus 20% if Reynolds number is greater than 10. This is the case of the use of this particular formula. Now, another one, this is for laminar flow. This one is for laminar flow also for fluids inside pipes. And in here, you have the Nusselt number, which will give you the HA. In here, it already gives you the formula in finding convective heat transfer rate. So first, find the HA from this particular equation. And then once you have the HA, use this particular formula. So either you use this one or you use this fragmented form of the general equation that you have here. Again, this one is for laminar flow. Meaning, class, allow me to speak in our dialect, ini siya gamiton mo together with this particular formula. Because this formula will tell you of the HA value that you will substitute in here. Again, for laminar flow. So T sub BI and T sub BO together with T sub W and delta T sub A are all defined in here. So the average arithmetic mean temperature. When we speak of arithmetic mean temperature, simply put, class, the average lang i-add mo kag i-divide sa 2. That's average arithmetic temperature. Now, the inlet bulk fluid temperature and the outlet bulk fluid temperature are normally stated by the problem. And of course, you have the wall temperature as T sub W. So that's for laminar flow. Of course, we should have for turbulent and something in between the two. So let's see. Now for turbulent flow, that is when the Reynolds number is greater than 6,000, this would be the Nusselt number equation that you will use. Very different. I will go back to my formula. Very different than the one that we have here by Sider and Tate. Okay, so first and foremost, class, before you use a particular formula for Nusselt number that will give you the H that you will substitute for the Q, establish first the regime. So, ano ginaunahon mo gali solve? Unahon kung gigali ni solve ang Reynolds number. Kay dira ako mabalaan kung laminar siya o kung turbulent or somewhere in between. Once I have that already established, then I can choose the particular formula for the Nusselt number that I will solve. So in this case, this is for your turbulent flow in pipes. So this is for Reynolds number greater than 6,000, and this is for Prandtl number on the range 0.7 to 16,000. So hindi siya pwede magsubra 16,000, hindi man siya pwede mag less than 0.7. So your Prandtl number should be within this range. And your L over D ratio should be greater than 60. So this is your condition, or this rather are your conditions that you need to check before you can use this particular Nusselt number formula. Just like, I go back again, this one to emphasize, this will be your conditions. That way you can use this particular Nusselt number formula for laminar flow. This one is for turbulent flow. Okay, let me move on. And this is a sample problem that we can use for the formulas that I have mentioned a while ago, that I have read a while ago. Now, what will happen tomorrow, class? Because let me just stop sharing, huh? But before I stop sharing, do you have any questions so far with the formulas that I have discussed with the overview of convective heat transfer? I think you won't have any because I haven't yet started with the sample problem. I think you may have more later on, or things will be clearer once I already use the formula in solving a problem. So I will stop sharing now. Okay. And I will stop recording because I will be discussing the schedule.